Nice. This week is go through the structure of a PLC and as much as you need to know about the internal workings, a little bit about how the inputs and outputs work in terms of interfacing with the outside world. Okay. Also going to dip back into last week's notes and go through formally about the different types of logic instruction and actually how the detail of what a ladder rung must and can't contain, and also go through how the timers and counters work. Okay, that way people who are a little bit quicker have got the opportunity to move on now and do some of the latest stuff in here and get on the timers and counters so they can press on. Okay, so in this morning's group I spent quite a bit of time this week up front here covering that material, and then there was about an hour or so, hour and 20 minutes left at the end once you had a break to actually have a go at some practical. All right. So, structure of a PLC. Generally, to the level of detail you need to know, you can divide it into 4 basic sections: an input interface, an output interface, a processing unit, and a memory unit. And they're kind of connected together like they are in that diagram. We've got our input interface here that feeds information into the processing unit. The processing unit feeds information to the output interface and also sends stuff backwards and forwards from the memory unit. Yeah. So then, looking at the detail of each of those, the CPU is like the brains of the whole PLC, and that's no different really internally, that CPU, than what you would have in your personal computer, your smartphone, your iPad, or anything else with that kind of functionality. Yes, there are different flavors, but in essence it's doing similar tasks. And what that does is it retrieves and processes the control program from the memory unit and deals with that in terms of what the current status of the inputs and outputs are, and a bit more detail of that later on in this session. The memory unit, 3 main functions: stores the control program that you write, it holds the images of the input and output status, and a little bit more about that later, but it holds what the latest state of all the inputs and the latest state of all the outputs are in memory. And that's quite key to the way that a PLC actually operates in terms of running your program, as we'll go through in a little while. And then it also holds any other data associated with the PLC's operation, i.e. the most recent input and output stored states, the current value of any timers, counters, and so on, and other data registers information that's important to the program's operation. Yeah, so that's all stored in memory. But without the input interface, and indeed the next bit, the output interface, none of that would do any useful work. So our PLC needs information about what's going on in the outside world so it can act on that and then control something else. So what the input interface does is it takes signals from things like sensors, switches and so on, and it indicates their current state to the CPU and stores it in memory. Input signals are usually 24 volts DC, although you might find some systems usually more expensive because they don't sell so many, is the general reason. 5 volt DC, 110 volt DC or 110 volt AC inputs. But generally, if you go out and buy a kind of bog standard PLC of any manufacturer, the input voltage is going to be 24 volts. To protect the internal workings of the PLC, the processor and other internal workings, the inputs are what's called opto-isolated. What that means is you connect your switch via a power supply. I'm going to put a battery in there. There's a power supply to the input terminals like so. When you turn that switch on, it turns on an LED in the input stage that is detected by a photo transistor and actually turns on the actual input inside the PLC, let's say X1. What that means is there's electrical isolation between this circuit and that circuit. So any voltage spikes, transients in there, will not damage the internal workings of the PLC and make the whole program crash. So it provides that kind of opto isolation. And all of that bit is in one kind of package. You can't see inside it. You can't see this LED light up. It's all encapsulated in its own package. Opto isolators. There's usually, and there is on ours, there are the numbers on the front panel, but there's little LED indicators to tell you whether the inputs are on or off as an extra indication, aside from the monitor and using the programming software. So you can actually look and see, is X1 on, yes or no, from the LED. There's further complication in terms of input sensor wiring, especially when we come to electronic type sensors. If we look at this diagram, we have a power supply, plus and minus, for our PLC inputs. Now that might be built in if you buy one of the mid-range or the low range, have a built-in power supply for the inputs of 24 volts. If that will not supply the current you need for all your inputs, then you can add to your own 24 volt power supply. But whatever it is, there is a 24 volt power supply. So if we take a plain, normally open push button like this one here, all that does when you turn that on is supply the positive through that push button to the input terminal there and turn it on. However, if you've got the electronic type sensors, like a capacitive or an inductive type sensor, or an optical photo eye type thing, they need a power supply for the electronics. There's also two different types. This one is actually connected to the positive there and the negative at the bottom, so it's got a power supply. And then when you put something in front of the sensor, piece of metal if that's inductive, okay, it turns this transistor on and allows current to flow through there and turn that input on. So they need, not only do they supply current to the input, but they also need current to make the sensor electronics work. Michael? Yeah, the inputs sense the current state of the machine. Yeah, so you use sensors for that. Outputs are what you use to turn motors on, to turn lights on, to turn hydraulic valves on, pneumatic valves and so on. Okay? And your program is the bit in between that, and we're going to look at an example in a little while that actually says what happens when certain inputs come on. We do this with these outputs. Yeah? Okay? So that's a general. There's two different things. You've got plain mechanical type switches that just supply a positive, in this case, to the input terminal. But you'll also have sensors that are 3 or more wires because they need a power supply. To further complicate inputs, they can also be what's called syncing or sourcing. The example you've just seen was a syncing type, like this one here, a sourcing type, sorry, like this one here. A sourcing type input actually has the transistor inside. It's a PNP transistor connected to V+. It's also got a negative, give it a power supply, V minus down the bottom, and then when you cover the sensor up, it turns that transistor on and current flows from the sensor into the PLC input, let's say X1. That's called sourcing because it provides the source, the positive. Yeah? The other type is called syncing. What syncing does is it still has a plus, V plus there, still has a minus to give it a power supply. The transistor is an NPN type where the current flows out of the PLC input down through the transistor to the negative rail. It effectively provides the negative to the PLC input. Okay, it sinks the current. So one provides the source, the other type provides the sink. Now, with our Mitsubishi PLCs, and I don't know about any other manufacturer, you can have either sinking or sourcing, but you can't have a mixture of both. You do the whole wiring scheme slightly differently to account for either sinking or sourcing inputs. So you don't have to buy a PLC with sync or source inputs, but you can only use one scheme. Yep, Michael. I'm not sure how they would. Are you saying on some more expensive ones you might be able to mix? You might be able to, but you could get problems doing that. I've never seen a setup where they mixed both syncing and sourcing inputs. The most common are the sourcing ones, I would say. I've only ever worked on one manufacturer's machines where they went syncing inputs. I have no real idea what might be the advantage of one way or to be fair. I don't really see where one might be an advantage over the other. Okay, but there might, out in the world there somewhere, there might be. Output interface. What the output interface is the other half of the PLC's interaction with the outside world. It takes the information from the processor that an output needs to turn on or off, and it acts on that. So it will turn up motors on and off, lights on and off, valves on and off, and so on. Generally, two different types of output, although you could come across a third, which is a solid state relay, similar in operation in a way to a transistor anyway. Some manufacturers do them, others don't. Relays, both methods, relay or transistor, have their advantages and disadvantages. Relays, advantages, that they are cheap, they can take AC or DC current and a variety of different voltages in general, and usually a higher current than transistors. Their disadvantages, they got a mechanical life, so the expectancy, because they're a mechanical operation, they got moving parts, they can wear out mechanically. Secondly, they aren't as fast as transistor outputs in operation. And on the next slide, we'll just look at the differences in speed. So they're slower and they wear out mechanically, but they're cheap. Okay, they provide inherent isolation from the internal workings of the PLC. Transistors, they got opto isolation, similar to the inputs. in the opposite direction. They're much faster. High life expectancy because they don't have any moving parts. But DC only, and a limited voltage range, which is detailed on the next page. Relays 5 to 250 volts AC. This is typical. This is pulled from Mitsubishi stuff, so not all manufacturers will be the same. Or 5 to 30 volts DC, 2 amp resistive load, 80 VA inductive. Response time approximately 10 milliseconds. So 0.01 of a second. Pretty fast, but bear in mind we're talking about 0.2 of a millisecond for transistor. Much faster operation, if that's important to you. But we're restricted to 20 to 28 volts DC, and the current handling capability is considerably lower as well. However, you're going to be switching big motors. You're going to need a contactor between the output and that motor anyway, particularly if that's 3-phase. You won't switch 3-phase directly with a PLC. Okay, so that are different types of inputs and outputs, and a little bit about the internal workings of the PLC. Everyone reasonably happy with that so far? On the next slide, I just need to pause this. What we're looking about here is going to go through the way the PLC deals with your program and the implications around the way it deals with it. What happens is, when you turn your PLC on, the first thing it does is a few housekeeping tasks, including deleting the output memory, the status of the output in memory. So it clears that. And I did say that the memory stores a copy of the output status and a copy of the input status. When I say status, I mean whether they're on or off in terms of digital inputs and outputs. Okay. Then the first thing it does is it polls or looks at the state of the input terminals. That's all your X terminals. And it records their status in memory, so it remembers whether they are currently on or off. Yeah? What it then does is go through to instruction 1 of your program. Okay? And between there and there, it only changes, it uses the current image of inputs, which could have changed, remember, to process the internal image of the outputs. So nothing output-wise changes until it gets down to the bottom. So if we've got a simplish program like this, Y3, like that. What it does is, first thing it does is says, look at X1. Is X1 off or on? Let's, for argument's sake, imagine that at this point X1 was on. So it looks at that and it says, oh, that's on. I've got to turn this on. So it stores the fact that output 0 has got to be turned on, but it doesn't do it yet. It then goes through to the next line of the program. Is this one on? No, so don't turn that on. It then goes through all your other steps of your program until it finds an end. Yep. It then steps through into that and transfers the image of the outputs where we've got Y3 off, Y0 on, and it transfers that status to the actual outputs. So it will then turn the lamp, if you like, connected to Y0, it will then turn that on. So up here, at this point in the program, it didn't turn it on. It does it at the end. Very fast, but nevertheless, there is a delay. There's a consistent delay. It's going to take the same amount of time every time it does it, which is important. Then it goes back to the start and records the input status again, and then goes through. Typically, I don't know, 5 milliseconds to do a whole scan. Just depends on how many instructions you've got and what they are, because every instruction takes a certain time to actually execute, and depending on how complex it is, it can take more or less time. So it is a variable, but once you've written your program and your program's a certain size, that time doesn't change. However, there are some implications in terms of that scan time. Just going to clone the page for a minute and get rid of some of this writing I put on there. Right, one of the implications is what happens if you get very, very short pulses on your signals. It's possible that a very short on-time pulse could be missed. Think about the situation where we come to this stage, poll the inputs, and X1 is off. It's stored the fact that X1 is off in memory, okay, and then imagine that this is not the first line in the program. Let's imagine that's line 30, and you've got a load of others before it and some more after. Yeah. So it's in this area up here doing some work, and at that time X1 in real life turns on, but in there it says it's off. Okay. If that doesn't stay on until it goes down the bottom round again and pulls the inputs, you completely miss that input pulse, because that's come on, and then we get to the bottom of the program and it goes off again. All it's going to be stored in there is off. It will miss that input. If that's meant to be counting something, that will miss it. So very, very short pulse times can be missed by these programs. Okay, probably not going to be an issue for any, it isn't going to be an issue for any program you write in here, but you should be aware that this is how the system operates. Okay, it's also why you'll get issues with something that we're going to talk about in a little while that happen if you double coil. You put the same output on twice. You could effectively be turning it on and off in the same program scan. Doesn't like that at all, and it will stick on whatever you last told it to do. Yep. The other implication is if an input changes right near the start of the program, but after it's done this bit, you've got to go through the whole program scan, back to the start, pull that new changed input, and go all the way to the bottom again, almost 2 complete scan times before the output actually acts on that input. And again, could be milli or microseconds, but in some applications where speed is at a premium, that might be an issue. And so you should at least be aware that this is how PLC operates. But it's done that way because it makes it consistent. Yeah. The only way round that, if a speed is an issue, is to use something called an interrupt. So it interrupts the program and goes off and does something else and then comes back again. The issue with interrupts is they are very difficult to test under every possible scenario that might happen. You know, with people pushing certain buttons at certain times, or some kind of alarm happens on a machine. If there's interrupts involved, difficult to test them fully. So you kind of avoid them unless you absolutely have to use it. All right. So that's a little bit of an overview of, and sometimes you'll hear this called mass I/O copying, because what you do is take a mass copy of the inputs, deal with them, and then en masse copy them to the outputs at the end, and then refresh and keep going round and round and round that all day long. Very fast. Okay, everyone happy with that? So there's a page that kind of summarizes what I've just said. Main advantage of continuous scan is that the program scan time is fixed and consistent. However, an input change that happens just after the input scan will not be recognized for a whole scan time, and the associated output change could be almost 2 scan times. An input signal duration shorter than approximately 1.5 scan times has the potential to be missed. If it happens just the right time, it will get seen. If it happens at just the wrong time, it will get missed. Yeah? Not a major issue for the large proportion of applications, but you should be aware. And you might remember I said to you last week about the system I worked on where they had to put 2 processors in, and that would be because the single processor couldn't deal with all it had got to do fast enough, and that was because the machine had a lot of analog processing on it where it needed to keep constantly updating. All right. So, I'm going to do a useful little contrast between a traditional relay control system and then how that would be implemented in PLC parlance. All we got here is a simple start-stop of a hydraulic motor, okay, and a push button to send a stamp down, and the idea is a simple hydraulic press that will stamp the lid onto a paint can, for instance. Yeah, so it's got a stop-start for the motor, and it's got a limit switch to say the stamps hit the bottom, go back up again. So the basis of the way this circuit would work is you've got a controlled positive and negative, that could be 24 volts, could be 240, and you've got a 3-phase system to power your motor through a contactor. So we push this switch here, we get current down there through the normally closed stop button to that relay, which turns on and closes that contact. We've got a parallel path so that when we let go of the start button, the motor continues to run. And anyone already familiar with moving machinery and motor stop should be reasonably familiar with that circuit. So your hydraulics is running. You then push the stamp button, we get current down there through the limit switch to that relay. Difference between relays and contactors. Contactors have got high current contacts. Relays generally much lower current contacts. Which closes that because it's associated with R1. Our hydraulic valve, that closes. We get current down there. Valve turns on and the hydraulic cylinder starts to move down. When the hydraulic cylinder hits the bottom, pushes on that limit switch which opens it, breaks this current down here, so that disappears, that opens, valve turns off, and the cylinder comes back up again. So that's a typical control circuit using relays from the past. Okay, and that one turning on closes those 3 contacts and runs the motor by the way. Pushing this stop button opens that circuit, turns that off, and turns the motor off. If we want to transfer that so it's controlled by PLC, we're going to do it like this. Here's your motor start button, there, motor stop button, stamp button, and limit switch there. connected to X0, X1, X2 and X3. You've got your contactor for your pump motor connected to Y0 and your hydraulic valve connected to Y2. You then write a program that sits inside there that turns them on and off according to the state of those. Do you see what we're on about there now, Mike? Yeah, from your question earlier. So this is telling the PLC what state the equipment's in, and this is controlling the state of that piece of kit. The rest of the interaction, when them relays come on and go off, is dealt with by your program. Notice that this bit is exactly the same as it was before. And that would be, it'd be the same contactor and the same valve. But if we imagine we find that the lids aren't going on very well because the cylinder's going down and coming straight back up again, we want to delay it so it goes down, sits there and waits 2 seconds to make sure the lid is fully on before it comes back up. With this system, we simply reprogram with that time delay function in. If we want to do that with this system, we've got to cut a hole in the panel and put a timer in. We've got to take some wires out and put some new ones in. We've got to do a rewiring job. Not a particularly big one in this example, but we've got to do that nevertheless. Don't get the idea that you never have to do any wiring to change a PLC, because if you're adding a sensor or adding an extra output, you certainly do. Okay, but generally, if that's just how the things interact with each other, can quite often be done by changing the program in some way. So it does reduce the amount of work when you want to add functionality. Right, I'm going to move away from that set. So, makeup of a ladder rung. The two sides are your stiles, and then the rungs go in between. That's why they're called ladder rungs, because they look like a ladder. And every ladder rung must consist of at least one logic instruction over this side, connected to the left-hand end, maybe many more, but at least one, and at least one coil instruction. Okay, what we can do is we can turn multiple things on, so we can add to that Y3 and T4, K20, all turned on with the same logic. Yeah. What we mustn't do is have Y1 or Y6 or Y7 or any coil more than once in the same program, and more about that in a little while. Double coiling, and your program may well not work properly if you do that. It's not illegal, the software won't tell you about it, because under some circumstances, if you've got subroutines, you can have the same coil in two different subroutines, so it doesn't flag it up as a definite error. It's your responsibility not to do it in the same routine. So, structure of a PLC logic instruction. First of all, program instruction is represented in a ladder diagram by the instruction type, which is designated by the letter. And we'll go through what each of them mean at the moment, but in this case X is an input, and then a number that says which input it is, in this case input number 0. Okay, and then the instruction, which in the case of that example there is a normally open contact. So we got a device name, a device address, X equals input from the outside world. Device types for logic instructions. So we got our input there, but equally that could be a contact associated with an output coil. So a contact that closes when that coil is turned on, or opens when that coil is turned on. It could be a contact associated with a timer, or a counter, or an M relay. And M relays are internal relays. Again, a little bit more about that in a little while. But they're used for internal functions within your program. So T2 will be timer number 2, and Y4 will be output number 4, etc. Moving on from there, bearing in mind that we can have contacts associated with inputs, outputs, timers, counters and M relays. Two basic types of logic instruction. Normally open, that one being a normally open X2 contact. When we use the word normally, we mean what is its state when that input or device is turned off. So this one is open when X2 is off and closed when X2 is on. The other type is normally closed. That's closed when X2 is off and open turns on. So those two contacts there are mutually exclusive. They can never both be closed at the same time because they're associated with the same input and they're inverses of each other. Note when monitor and program, if the instruction has a blue square in it, the contact is closed regardless of type. So when you're monitoring, if you see it like that, that means X2, that contact is closed, it means that input must be off. Yep. And that one would be, as it is now, open. Building logic functions. Two basic types of logic instruction used. AND or series logic, series circuits, one switch after the other, and this switch and that switch and that switch have got to be on before that function happens. Okay, and then you've got or parallel logic, this switch or that switch before we turn on. We'll look at the two separately, then they can actually be combined and used in combination to create more logic complex functions, and also you can use the inverses, the normally closed and normally closed or. And in your notes there are exercises for you to have a go at each. So the first one of those is AND. Ladder rung will, if the input X2 and the input X3 are on, turn on the output Y2. And this is a truth table for all the different possible combinations of those two switches. So 2 off and 3 off, 2 off and 3 on, 2 on and 3 off, 2 on and 3 on. And what should the output state be for each of those possible combinations of those two switches? And then when you test that program, you test against the whole truth table. So you don't just check that the light comes on when you turn both switches on. You check all three of these possible combinations of those two switches. It's along the lines of not just making sure your program does what you want it to do, but also that it doesn't do what you don't want it to do. Yeah. So if there's a specific thing that mustn't happen, you need to check to make sure it can't happen, as well as making sure what you want to happen does happen. Alright, so when you have a go at these, if you haven't already, enter the program and test it against the truth table, modify the program so you put an extra AND instruction in, and making sure that you have to turn all three switches on to get the light to come on. And then on the next page, It looks at what happens if we change those and the AND instruction to normally closed. And what that's done is it's moved the only on condition from the end to the beginning. Both switch, the light will only come on if both switches are off. And again, there's the opportunity to have a go, and it's really worthwhile making sure you monitor these programs and understanding how they work, why they do what they do, because it will help you when you come to design more complex logic later on. Then we have OR, which is the parallel logic. It's where we end up with more than one path through to the end. We can go along the top, or we can come from here. So it's switch 2 or switch 3, and you'll notice there's 3 of the conditions in the truth table that will give you a light on condition. When one is on, when the other switch is on, or when both are on. Okay? And later on, one of the challenges is for you to get the functionality that would give you just those 2 conditions. So when one switch is on or the other, but not both. Okay, and pretty much guarantee that you've got a circuit that functions that way in your house. And there's a question there about, can you think where that is? Okay, so have a go at the exercise and see if you can think where you might get that functionality in your house. And it has got a special name. It's called exclusive OR, because you get the OR function, but not both. And then there's have a go with the OR function and inverse or normally closed. Again, and at the end of that, there is some extra exercises for you to have a go at. Okay, in this one, it's where we're combining both the AND logic and the OR logic. So we've got 2 elements ANDed together, X2 and X3 are on, and we got a X4 and a not X5, a normally closed X5 ANDed together, and then we've ORed together that pair. So we'll get the light on if both of these are on, or if that one and that is on and that one isn't, which is what it says there. Write your program to turn a light on when switch 2 and switch 3 are on, or when switch 4 is on and switch 5 is off. Yep. So to test for off, you use a normally closed contact, generally. Test for on, you use normally open, generally. So there can be exceptions. And then the end of that set of notes, there is a challenge and an extra challenge. This is the extra challenge with regard to the exclusive OR circuit at the end here. So if you haven't already done those, and I think there might have been 1, maybe 2 people in the room last week that had gone through most of that, I've got something else for you that we're going to go through now. So I think, if I remember rightly, that is the end of that set of notes. Yes, it is. Okay, so make sure you get to the end of that and have had a go at those exercises before you move on to the practical that's in the new set this week. Internal relays, M relays. Mitsubishi PLCs have a large number, and other manufacturers do, of internal relays or M relays. Their internal logic, they have absolutely no connection with the outside world. You can't use them to directly turn motors, valves, lamps, and so on and off. Use them indirectly because you use M relays to switch Y relays, but only the Y relays will actually turn the real outputs on and off. Okay, but there are 384 points between M0 and M383. Another 1152 M relays from 384 to 1535, which are battery backed. That means they'll hold their status if you turn them off. Another 6144 general internal relays, and then you've got some special type, which we'll look at one or two of in a minute, but they're 512 points there. They're not, you don't use them as outputs, you use their function, and I'll explain why you might want to use that. The general idea with M relays is they help you to simplify complex logic, break it down into simpler steps, and also the key for what you're going to be doing is avoiding the situation of what's called double coiling, using the same Y output or timer output more than once in your program. And you'll do an exercise to show what happens when you double coil and the possible what will happen with your program if you could happen with your program if you do that. So, internal relays to simplify logic. If we look at that bit in blue there, it's a complex piece of logic. Let's imagine that's on our paint stamp can, right? And that's all the logic that determines whether all the guards are closed and everything's ready to move. If you didn't use the M relay like this, you'd have to put that piece of logic in every rung of your program to make sure the guards are shut. So if we look further down here, pump run can't run till the guards are shut. So we'd have to put all the 8 instructions there in here in place of that M1 relay. And in there, and in there. Mike. It's like a little subroutine, yeah. We use all that logic to turn on that M relay and latch it, for instance, in some way, so the guards are shut, right? And we just put M1 in each of the ladder rungs. So effectively, we've saved 8, 16, 24 instructions. Instead of 24, we've got 3 instructions. And we've simplified it, it's easier to understand. Yeah? So, use of M relay saves repetition of complex logic that is required in more than one part of the program. Okay? So you're probably going to find that you'll have a need to, at least at some times, use internal relays for complex logic. Yeah? The issue of double coiling. So we're talking about this part, the coil part of an element instruction. You can have M1 over here on this side, on the left hand side, as many times as you like. But you can only have M1 or Y1 or T1 or C1 coil once in your program. Thou shalt not double coil. However, it's not completely illegal because in some advanced programs you can do it if they're in different subroutines. So it doesn't pick it up. Makes it your responsibility to actually not do double coiling. The following example will illustrate the implications of double coiling. You're not being asked here to write this program. Okay? What it is a motor. We've got a start and stop button and a switch. And if the switch is in one position, you start the motor, let go, and it runs as normal. Switch in the other position, start the motor, and then when you let go, it stops. So it's got an inching function. So you could jog the machine along, or you can have it run permanently. And we use a switch to switch over between those two functions. An initial design for that, and when you get to this bit, I want you to enter this program and monitor it and test it against the functionality. So the idea is here's the start push button, there's the inch or run switch, So if that's turned into run mode, this is the stop button, so that'll be closed because you're connected to a normally closed push button. You're going to use the little switch panels to do this. So instead of a motor, you've got a light. That makes no difference. When I push that button there, that will turn on Y0, close that contact, so when I let go, that light will stay on, or that motor will continue running. Yep, so that's feasible. Then we write another line of program that says, if the X2 switch no, because when you wire stop buttons, Mike, you wire them normally closed. Remember, if you remember from last week, on your rigs, the red button, the stop one, X1, the input is on when you got your finger off it, and it goes off when you push it. Yeah? They're done that way because that means it's fail safe. If your machine is running and the wire breaks off your stop button, the machine stops because you're losing that input. So stop functions are always wired normally closed in a loop. So if you break that loop, you actually stop the machine. It's called fail safe, fail to the safe condition. Yeah? Otherwise, you imagine that stop button sitting there as a normally open stop button, like this, right? Sitting like that, with the machine running, right? That wire falls off there, so it's not connected anymore. Someone wants to stop the machine, they hit that stop button, it's not going to stop. Because it didn't fail safe. The way I should cover that is that in the normal condition, that contact is closed. While my finger's off that red button on those switch boxes, that contact is closed. Because the X1 input is on. When we get over on the practical, call me over and I'll show you what we mean. Okay? So the other option, the other functionality, is when X2 switch is off, i.e. it's in the Introdcution mode, we push this button, the motor runs, we let go, it stops. Right? The problem with this program is, when we try to run in auto mode, i.e. that switch is on, if that's on, that one must be off. Everyone agree with that? Because they're opposites of each other. We think this will work, but what happens is, remember your program scan time now, and how it scans the program. We push this button, the program tells it to turn that on, but then when it interrogates, so that line says in memory, turn on Y, but not the real Y0 yet, because we ain't got to the end instruction. It then comes along to your next line of program, and this line of program says, turn it off. So it never comes on. Yep. Agreed? Okay. And then, if we try and use this half, it will work. In actual fact, if you change the order of those in that order, the Introdcution will work, but the start-stop won't. And if you put the Introdcution before the start-stop, the Introdcution won't work and the start-stop will. And it's all about that scan time, and because it doesn't update the output until it's been through all the lines of the ladder program. So you're actually turning that on there, but then an instant later, you're turning it back off again. Yeah? So the way round that situation, or one way round it, is to use an M relay for each of the two functions. That line is the stop-start, turning on M0. This line is the inch line, turning on M1. and then we just use the ORed M1s, either MO or M1, will run the motor. And you've avoided the double coil. Don't worry if you don't get this at the moment, because you may not, but hopefully you will when you have a go, when you actually see that in operation. You could solve the problem by putting all the logic for the motor in one ladder rung. However, this solution allows the program to be structured on larger programs, will provide added benefits for fault finding. Because what I tended to do was have all my outputs in one section right at the end of the program. So you can look at multiple outputs in one place and have all the logic that controls them up at the start. So it allows you to structure and simplify your program, make it more understandable, so you can interrogate it in stages when you want to fault find. Okay, now when you're having a go at that, don't worry about the fact that my version's got comments on it, but do save that as double coil problem solved in your area, because we're going to use that next week to go through how to document a program, put these comments in, name all these elements and get the documentation right. Okay, so when you get to that bit, please save it as instructed. Okay, not much longer before we take a little break, and then you can have a go at the practical for the week. These special function relays, M8000 onwards, we won't use many of them, but you might have a need to use one or two of these early ones. Difficult to see on here, but look at your notes. M8000 is run monitor, normally open. What that is that's a contact, M8000, that is closed when it's in run mode, when the PLC is in run mode, and that's open when a PLC stops. And then you've got the opposite of that, M8001 is a normally closed on run, so that opens when you start it, switch to run mode, and closes when you switch run mode off. The next two do a short pulse on switching to run or switching to stop. A short pulse, whenever I talk about a short pulse, we're talking about one scan time. The output turns on for one scan time and then off again. Very useful for doing initialization type things, resetting all your counters, setting up data registers and things. Use that short pulse, because then, as you're going to see in a minute, if you leave the reset instruction on a counter, it won't count. So if you use a short pulse to reset it, you're kind of guaranteed that you're not going to miss any counts. And then you've got four here that are useful clock pulses. You've got a 10 millisecond, a 100 millisecond, a 1 second, and a 1 minute clock pulse. So on, off, once every of those time periods, 10 milliseconds, 100 milliseconds, 1 second, and so on. And back in the olden days, when there weren't so many hundredth of a second resolution timers, I actually used the 100 millisecond, 10 millisecond, sorry, clock pulse to create some extra 0.01 resolution timers for a particular application that are programmed. So we used a counter to do a timer function by using one of these clock pulses to actually pulse the counter. So you might find use for them, and all the rest are in the GX or FX series programmer manual. Timers. You've got 200 timers between T0 and T199 that you can set in 0.1 resolution steps, a tenth of a second. You've got 46 between 200 and 245 that you can set in 0.01 steps. You've got 4 between 246 and 249 that you can set to 1,000th of a second steps. And then you've got some retentive types. Retentive meaning they will hold their current state even if you lose power. You would want to think very carefully about whether that's what you want to do. before using those, but there's 6 of them. I've never used one. Okay. And that's how timers work. So it's a little program there, and this little chart tells you what happens. So when we turn X0 on, I'll use blue because that's what you're used to for the thing. When that turns on, we turn on the T1 coil, and the way this is put into the program is T1 space K 30. And on the standard timers, that would give me a 3-second time, because we're on a 0.1 pulse, remember, with the standard timers. So we've got to multiply what we want by 10 to get our constant. The other thing is, we could change that constant for the contents of a data register. And we'd do that if we were trying to interface with an HMI, so that our operator could actually change that 3 seconds to 3.5 or down to 2.5 and so on. It would then use, instead of using a constant, it would use the contents of a data register as its time reference. Okay, so when we do that, that turns on, and then it starts to count to 30. When it hits 30, this contact closes, and that output turns on. So it's like a 3-second time delay between switching the input on and the output actually coming on. So it's an on-delay timer. Yep. If we look at this chart, you'll see if you don't allow it to time for the whole 3 seconds, i.e. that goes off before the 3 seconds is up, the whole thing actually resets back to nothing. Okay, and what happens when we do reach 3 seconds is that's when the output turns on, and then that stays on until we turn this input back off again. So we've got 3 states. We've got timing, which is when that 30 figure is counting up, and you can see that on monitor. You'll see that later. When you monitor a timer, you can see the count process happening. The timer is timing. When that time is up, you say that's timed out. When it times out, open contacts close, closed contacts open. And then when you take this signal off here, the timer resets back to nothing. Yeah? So if you want to keep that timing, this has got to be a permanent switch, or you've got to switch it on and latch it in some way. Okay? And you might find that you need to do that at some point. Remember, output for T1, that bit can only be used once, but you can have as many contacts on that timer as you like, up to the memory limitations of your PLC. Yeah. So then there's a basic timer programming task for you to have a go at. I'm not going to go through that here. See if you can do that. There's a second one around a light going on for so many seconds and off so many seconds, so a cycling timer. Worthwhile hanging on to that, because when you have a go at your pedestrian traffic lights, you're going to want a flash and amber light. Yep. For the return from cars being stopped to flash and amber and then green again. Okay. Counters, again, a number of different types. There's 16 general points. There's 184 latch type, which are battery backed, and then there's some more high-speed counters and so on. So you've got some 16-bit up counters and some 32-bit bidirectional. That means you can get them to count up and down. Retentive timers hold their value when you turn the PLC off. Counters work a little bit differently to timers. They don't reset themselves. You have to do a separate reset instruction to reset a counter. and that's done like you did the timer. It's in square brackets instead of round ones, and it's RST space and then the counter number. So in this case, when we turn the input X0 on, like so, we reset the counter. From the diagram, you should note that while X0 is on, it won't recognise any counts. So while that reset instruction is energized and blue, you can try to count all the time, but it won't count them. The way you count is you need that to be off, and then every time we turn this one on and off again, that's these steps here, we count up one step. Okay. If we reset here, we'll go back to nothing. Once we get to 10, that closes and that output turns on. And until we reset, that'll miss any counts. So we need to make sure our reset is done in the right place so that we can carry on counting the next batch of product if that's what we're doing. So the implications of when you reset your counters needs to be thought about a little bit carefully in terms of what's the application you're trying to achieve. So not a lot different to counters in terms of the way you program, but you do have to have this separate reset instruction. And then in your set of notes, there's some counter programming tasks, simple counter and basic counter number 2. And then that goes into the piece about documentation that probably will start off with as part of next week's practical. Okay? So